Okay, in this lecture we'll continue moving through our section 3.1 material on integration by parts. Now in the first part of this lecture, we had introduced the technique of integration by parts, and we mentioned that it's often used to integrate products of functions which can't be simplified, to integrate functions where maybe a logarithm is involved and a substitution won't work, or to integrate functions involving an inverse trig function where a substitution wouldn't work. So in this next example, we're going to consider a type of integral which is sometimes referred to as a loop integral, for which integration by parts is applied more than once, and we end up getting stuck in what would appear to be a loop where we would have to apply integration by parts repeatedly. However, there is a technique that involves some algebra which will allow us to evaluate these types of integrals. Now, before we look at this example, I'll mention that this type of problem, which is going to be an example of a loop integral, will occur when you're trying to integrate an exponential function times either sine or cosine of x. So as soon as I look at this problem, I see that it involves an integral of a product of two functions, e to the 2x and cosine of x, and I can't simplify this product in any way. So that should suggest to me that I'm going to use integration by parts. And our first step in the method of integration by parts is to choose part of our integrand as u and part of our integrand as dv. Now for this particular type of problem, it doesn't matter what function we choose for u. I'm going to take u to be e to the 2x, in which case dv is cosine of x dx. However, if you want, try reversing what my choice for u and v was. So in your version of the problem, try choosing u as cosine of x and then dv as e to the 2x dx. And as you work through this, you'll see at the end that your answer will be the same as mine. It doesn't matter what we choose in this case. Now, once we make our choice for u and dv, our next step is to find du and v. So by the chain rule, du would be 2e to the 2x dx, and v would be the antiderivative of cosine x, which is sine x. So applying the integration by parts formula, the integral of e to the 2x cosine of x dx is equal to u times v, which would be e to the 2x sine x, minus the integral of v times du, which is 2e to the 2x sine x dx. So now this integral that I'm left with after applying integration by parts is a product of two functions. I have 2e to the 2x times sine x, and I can't simplify that product in any way. So again, that suggests that we might try integration by parts. So after I apply integration by parts the first time, I'm left with an integral that will require integration by parts again. So for this new integral, let us choose a new value for u and dv. So sticking with the choice that I made in the beginning of the problem, I chose, for my first integration by parts, I chose u as the exponential function. So I'm also going to choose u as my exponential term here. That was 2 times e to the 2x, in which case dv is everything else, sine x dx. So finding du, by the chain rule, I would have 4e to the 2x dx, and v would be the antiderivative of sine x, which is negative cosine x. So let's see what we have. Our integral that we started with, which was e to the 2x cosine x dx, is equal to e to the 2x sine x, and then minus, well, for this new integral that we obtained, we're applying integration by parts again. So we would first take u times v, which is negative 2 e to the 2x cosine x, and then we would subtract the integral of v times du. Now let's see what we have. So v times du would be negative 4 e to the 2x cosine x. But we're subtracting that quantity, or the integral of that quantity, remember. So subtracting the negative 4, we get a plus 4 times the integral of our e to the 2x cosine x dx. Or simplifying a little bit, if I distribute that negative through my set of square brackets, I have plus 2e to the 2x cosine x, and then minus 4 times the integral of e to the 2x cosine x dx. So after I apply integration by parts a second time, I'm left with this new integral, which would be the integral of e to the 2x cosine of x dx, which is a product of two functions, an exponential and a trig function, so it can't be simplified. So we could try integration by parts again, but you might notice at this stage in the problem, well, this integral that I have down here, that is the integral of e to the 2x cosine x dx, is exactly the integral that we started with. So after we've applied integration by parts twice, we get an expression that involves the same integral that we started with. So this is why it's referred to as a loop integral. After applying integration by parts a number of times, we get back the same expression that we started with. So how do we proceed from here? Was our initial integration by parts 2 times all a waste of time? Well, arguably yes, but we see here that we are able to solve for this integral algebraically. So let's think about how we can do this. Looking at the last line of work that I have here, I have this integral that I'm interested in is equal to e to the 2x sine x plus 2e to the 2x cosine x, and then I've got minus 4 times the same integral that we started with. So from here, I'm going to use algebra to solve for this unknown integral. Let's think about it like a variable. I have this integral, maybe if I call it a variable, say I is equal to the sum of a couple of terms and then minus 4 times I. So to solve algebraically for this integral I, well, I could group all of the terms involving I or this integral together. So in other words, if I were to add 4 times this integral to both sides of this equation, I would have 5i, or 5 times the integral of 2x cosine x dx is equal to e to the 2x sine x plus 2e to the 2x cosine x. So I was just grouping all of the terms involving that integral together. So now to solve for this integral that I'm interested in, Well, I just have to get rid of the multiplication by 5 out in front. So I can divide both sides of my equation by 5, and I'm left with the integral of e to the 2x cosine x dx is 1/5 e to the 2x sine x plus 2/5 e to the 2x cosine x. And since this was an indefinite integral, I can't forget to include my constant of integration on the end. So at this stage, we've managed to solve for that integral of interest. So this is the idea behind a so-called loop integral. Is after we apply integration by parts a few times, in this case twice, we get back the same integral that we started with. However, it was being multiplied by some constant out in front. So if I then treat that unknown integral as a variable, I can solve for that integral using algebra, and I'm able to obtain my answer. So again, this type of integral will occur when you're trying to integrate the product of an exponential function and a sine or cosine function. So let's look at some other examples. In these next couple of examples, we'll consider integrals or antiderivatives that involve multiple techniques. And we've actually already seen some of these when we were considering the examples with the inverse trig functions. So here in our next problem, we're told to evaluate each integral by first making an appropriate substitution and then using integration by parts. So there are certain problems where we have to use multiple techniques of integration, such as substitution and integration by parts, and we'll see some examples of those here. So in part A, I have the integral of x cubed times e to the x squared dx. So when I look at this, I see right away, well, my integral involves a product of two functions, which can't be simplified. So I might try an integration by parts right away. Now we'll see that this won't work out. Now why not? Let's say that we choose u as our x cubed, so that dv is e to the x squared dx. Well, du would be 3x squared dx, and v would then be the antiderivative of e to the x squared dx. However, we don't know what that antiderivative is. To try to evaluate that integral, we could try a substitution. However, this integral cannot be evaluated analytically. Now we could try reversing what we call u and v. So let's say that we reverse our choice and we let u be the e to the x squared term, so that dv is x cubed dx. Well, du, using the chain rule, would be 2x times e to the x squared dx, and v would be 1/4 x to the 4th. So applying integration by parts, we would have u times v, or 1/4 x to the 4th e to the x squared, minus the integral of v du, which would give us 1/2 x to the 5th times e to the x squared dx. So looking at this new integral that we're left with, well, it involves x to the 5th times e to the x squared, which is even worse than what we started with. We only had x cubed times e to the x squared. Now we have an even higher degree polynomial times e to the x squared. So based off this work, it appears that integration by parts is not the way to go from the beginning of our problem. So what other technique could we use? Or maybe a more important question would be, when we look at this problem from the beginning, why might we choose a technique other than integration by parts at the start? And my answer to that is, when I'm looking at this integrand, I see that it involves a composite function. It doesn't involve just e to the x, but e to the x squared, e raised to a function of x. And whenever I see a composite function as part of my integral, I should immediately think of a substitution first. And also this problem statement tells us by first making an appropriate substitution, we should proceed. Now, if we weren't given that direction, how do we know to make a substitution first? Well, by recognizing that our integrand involves a composite function. So let's start by making a substitution. I'm going to say let w equal x squared, the inside function in that composition. In which case, dw would be equal to 2x dx. And so dx is equal to dw over 2x. So rewriting our integral in terms of w, I would have the integral of x cubed times e to the w, and then dx, which was dw over 2x. So simplifying a little bit, well, I can pull out a constant of 1/2, and then I have an x cubed divided by x. So canceling one factor of x in the numerator and denominator, I'm left with x squared, and then e to the w dw. So at first I'm stuck with this factor involving x, which is x squared. However, x squared is what we were calling w. So this is actually 1/2 the integral of w e to the w dw. Now once I have this integral in terms of w, I see that it involves a product of two functions which cannot be simplified. And it no longer involves a composite function at all. So our only method to proceed here would be integration by parts. And for this method, we're going to choose part of this integral as u, and the remainder will be dv. So here, I'm going to choose u as w, and then dv will be e to the w dw. So du is then 1 dw, and v would be the integral of e to the w, which is itself. So going back to our problem, we had the integral of x cubed e to the x squared dx, which we rewrote as 1/2 of the integral of w e to the w dw. So applying integration by parts for that integral, we would have u times v, which is w e to the w, minus the integral of v du, which would be e to the w dw. So distributing our constant 1/2, we have 1/2 w e to the w minus 1/2 times the integral of e to the w, which is e to the w. And at this stage, once I've evaluated all of my integrals, I can include the constant of integration plus c, since this was an indefinite integral. Now in our last step, I want my final answer in terms of the variable x instead of w. So let's take w, which was x squared, and substitute back into our answer. So we will have a 1/2 x squared times e to the x squared minus 1/2 e to the x squared plus c. So we see in this example a problem for which we first might have to make a substitution if our integral involves a composite function, and we would then have to make use of integration by parts to evaluate the new integral in terms of our new variable, in this case w. So let's look at another one. In part B, we have the integral of sine of square root of x dx. So when I look at this, immediately I recognize that this is a composite function. It's not just sine of x, but sine of square root of x, which suggests that we should try a substitution. So I'm going to let w equal the inner function in my composition, that is the square root of x, so that dw is 1 over twice the square root of x dx. And solving for dx, I have 2 times the square root of x dw. So rewriting my integral, which was sine of square root of x dx, in terms of w, I have the integral of sine of w, and then dx was equal to twice the square root of x dw. So at first glance, it looks like I get stuck with this term involving x, which was twice the square root of x. However, the square root of x is what we were calling w. So my 2 times the square root of x is actually 2w, and then I was multiplying by sine of w dw. So after I make my substitution, I have the following integral, and I see that it is the integral of a product of two functions, 2w and sine w, and I can't simplify this any further. It also no longer involves a composite function, so the only method I have to proceed is integration by parts. So we're going to choose part of this integrand as u. So here I will choose u as the polynomial part of my function, 2w, and dv is then sine of w dw. So calculating du, I would have 2 dw, and v would be the antiderivative of sine w, which is negative cosine w. So looking back at the integral that we're interested in, I want the antiderivative of sine root x dx, which was equal to the integral of 2w sine of w dw. And using integration by parts to evaluate that, we would have u times v, which is negative 2w cosine w, minus the integral of v du. So v du is negative 2 cosine w. When I'm subtracting that, I'll get a positive integral of 2 cosine w dw. So we have a negative 2w cosine w, and then plus 2 times the antiderivative of cosine is sine of w. And at this stage, once I've evaluated that integral, I can include my constant of integration plus c. And in my very last step, I'll substitute w, which was the square root of x, back in for my answer. So I've got negative 2 root x times cosine of root x plus 2 times sine of root x plus c. All right. So again, another example where we first might have to make a substitution if our function involves a composite function, and the resulting integral may then require integration by parts. So in our last example, let's consider a problem which will combine some of our Chapter 2 techniques on applications of the integral with this new technique of integration by parts. So for this problem, we are asked to find the volume of the solid generated by rotating the region bounded above by y equals cosine of x, and below by the x-axis on the interval from 0 to pi over 2 about the y-axis. So let's visualize our region here. For these problems involving solids of revolution, it is helpful to sketch our region of interest, which we were told is the region under the cosine x function. So at x equals 0, cosine of x is 1, and then cosine of x decreases and intersects the x-axis at pi over 2. So we want the region bounded above by this cosine x curve, below by the x-axis on this interval from 0 to pi over 2. So this is our shaded region of interest, and we're supposed to take this region and revolve about the y-axis. So here, since our curve is bounded above and below by functions of x, it might be easiest to think about slicing this region into vertical slices of a small width dx taken at a distance of x units from the y-axis between 0 and pi over 2. And we can see that if we revolve that vertical strip about the y-axis, a vertical axis, we would get a cylindrical shell. So using shells to calculate the volume of this solid would be given by 2 pi times the integral with respect to x, which would be over the interval from 0 to pi over 2 here. And then we would have the radius of our cylinder, which is x, times the height of our cylinder, which is given by the height of this curve, which was y equals cosine of x, times the thickness of our cylinder, which was dx. So we need to evaluate this integral, and we see that our integrand is a product of two functions, x and cosine x, and they cannot be, or this product cannot be simplified at all. So that suggests that we should try integration by parts. And our first step is to choose part of our integral as u. So here I will choose u as x, in which case dv is cosine x dx. So it follows that du is equal to 1 dx, and v is sine x. So looking back at our expression for the volume of this solid, we had a constant 2 pi times this antiderivative. So using the integration by parts formula, we have u times v, so that is x sine x, minus the integral of v du, which was sine x dx. Now here we have a definite integral from 0 to pi over 2. So when I rewrite my formula using integration by parts, this new integral is still being evaluated from 0 to pi over 2. And this first part of my function that I found for the antiderivative will be evaluated from 0 to pi over 2. So let's see what we get here. Continuing, we have 2 pi times, well, we had an x sine x, And then minus the antiderivative of sine x is negative cosine x. But since we're subtracting that quantity, we have a plus cosine x. And this antiderivative is being evaluated from 0 to pi over 2. So let's see what we've got. We have a constant 2 pi times evaluating at x equals pi over 2. We have pi over 2 times sine of pi over 2, which is 1, plus cosine of pi over 2, which is 0. And then we subtract what we get when we evaluate at x equals 0, which would be 0 plus cosine of 0, which is 1. So we would have, when we distribute, or let me maybe write it like this first, 2 pi times pi over 2 minus 1, or distributing, I would have pi squared minus 2 times pi. And this would be our volume of the indicated region in cubic units. So a little review of our Chapter 2 techniques combined with these new techniques of integration.